Okay, so recently in the last kind of couple of chapters and so forth, we've been talking about grams to moles and moles to grams. We talked about balancing equations in the last sort of chapter there. Also talked about all kinds of different types of reactions to take place and ways to classify them. And as we talked about last time, there are many sort of ways you can sort of classify the same reaction depending on sort of what you're looking at. So where we're going with, and I guess these chapters, some of this comes from parts of each of these chapters. We're going to talk about kind of putting those two things together, the balancing equations, the grams and moles. We're going to talk about stoichiometry and how to do stoichiometry problems, regular stoichiometry problems, limiting reagent type problems. We also will get into molarity, concentration, and titration type calculations, which is kind of like solution stoichiometry type problems. So we're going to kind of really focus in here on stoichiometry and doing those type of calculations. All right, so let us get into it here. All right, so stoichiometry just in general is a really fancy word, I suppose. It basically involves using a chemical equation to figure out how much, say, product you would make, how much reactants you would start with, in a sort of theoretical sense of if everything went sort of perfect in this reaction. If you started with, say, 5 grams of something, how many grams of a product would you produce? You could also figure out things like if you started with 5 grams of one reactant, how much of the other reactant would you need to sort of put in there with it? You could also use stoichiometry to sort of go backwards and figure out sort of where you started from. If all you know is how much you sort of produced. So if you know the amount of a product that was produced, you could use the equation. You could use stoichiometry basically to go backwards and figure out basically how much reactants that you started with. So stoichiometry allows us to use a balanced chemical equation to figure out things like how much is produced, which way, you know, um, if you started with a certain amount, how much to be produced, these sort of theoretical sort of things, if everything went perfectly fine in there. So what is stoichiometry? Sometimes people forget about stoichiometry, but really stoichiometry is just a sort of conversion, and it's a conversion factor basically. And for example, if we took an equation like, say, 2H2 plus O2 makes 2H2O. I think I balanced that right. So if we have an equation like this, stoichiometry takes advantage of what is sometimes referred to as the mole to mole relationship that you could get from an equation. And what is the mole to mole relationship? The mole to mole relationship basically means in a balanced equation, you could go to the coefficients, and the coefficients here would represent how many moles of each of those guys. So I think we saw that little couple different relationships in the last chapter where we could look at the coefficients, say 2 molecules, 1 molecule, or 2 moles, 1 mole. And we could use those relationships, really to come up with conversion factors. So, really stoichiometry is nothing more than sort of a conversion. The only difference is sort of where you get your conversion factors from. So it's like a normal sort of conversion. You go to a table, look it up, and it tells you, hey, there's 12 inches in a foot. In stoichiometry, we use the actual balanced equation as pretty much our conversion factor and where we get these conversions from. So from an equation like this, just a balanced equation, by the way, none of this will work correctly if your equation is not balanced. So it's really important always, as we talked about, to make sure that you do have a balanced equation. But basically from this one equation here, we could come up with several equalities. Basically, we could say that for every 2 moles of H2 I toss in there, I basically need to also toss in 1 mole of O2. The 2 and the 1 comes pretty much directly from the coefficients. Remember that if nothing's written here, It's assumed to be 1. And that's basically where they come from. We could also say that for every kind of 2 moles of H2 I put in there, I could expect to get out kind of 2 moles of H2O. Again, coefficients is where those numbers come from. And lastly, in terms of this equation here, we could also say that, for every 1 mole of O2 I toss in there, I should also get 2 moles of H2O. So you can think of stoichiometry kind of like proportions, like when you're making cookies or something like that, you got to put so much flour, so much chocolate chips, and all those kind of things in there to produce, say, a dozen cookies. In terms of a reaction, in this case, we need to throw in 2 moles of H2 with every 1 mole of O2 to produce 2 moles of H2O. So sort of the proportions. These are basically equalities. These are what are referred to as being stoichiometrically equivalent with each other. So when we talk about equalities, they're basically two things that are on different scales but represent the same amount. When we talk about something that's sort of stoichiometrically equivalent to each other, is they're not equal to each other in terms of numbers. So clearly 2 does not equal 1 and stuff like that, but they are equal to each other, like I said kind of previously there, in terms of proportion. Like this is how much you need to kind of toss in there to produce a certain amount. Now, when we talk about regular equalities like we did, which is regular with conversions and stuff like that, for every equality that you have, you basically could write 2 conversion factors. So from this equality, we could write for every 2 moles of H2, I got 1 mole of O2. Or again, we could do the opposite there. 1 mole of O2 gives us 2 moles of H2. For this guy, we could write 2 moles of H2 gives us 2 moles of H2O, or 2 moles of H2O gives us 2 moles of H2. And lastly, for this guy, we could write 2 conversion factors, 1 mole of O2, 2 moles of H2O, are 2 moles of H2O, and 1 mole of O2. So from this one kind of simple sort of equation, this balance, we actually have 6 different conversion factors that we could use in a problem. Would we use all these in a problem? The answer is no, we really wouldn't use all these in a problem. We would use the ones that are only probably one of them that we would need. But we would use them, again, like dimensional analysis, as a conversion factor to go through it. So since all the important stoichiometry relationships that we see here are mole to mole relationship, that also brings up a very important sort of conversion that we do a lot in stoichiometry, which is a lot of times we're given stuff in grams. So we need to take these grams to moles and remember that it is the molar mass that allows you to do that. Molar mass from the periodic table in grams per mole is the guy that allows you to do that conversion by going grams and again dividing by the molar mass will give you moles. I will also say that on the back end of a lot of these calculations, you're asked how much grams you produced, which means we also need to use the molar mass to go from moles to grams a lot of times on the back end of this calculation. And again, molar mass being what we use for that. In this case, we would multiply by the molar mass. The moles would cancel. We would end up with grams. So these conversions we talked about previously when we were talking about grams and moles, we definitely use a lot. Sometimes we use it at the beginning. Sometimes we use it at the end. Sometimes we use it at both times in these type of calculations. So for example, if we were looking at, say, this made up problem here, and let's just say, for example, that we produced 52 grams of water, how many grams of O2 did we start with? Well, when we do stoichiometry sort of problems and sort of basic stoichiometry problems like this one is, there's really kind of 4 steps that we want to follow when we do this. And we'll see it, I think, in a second here. But in basic stoichiometry problems, usually the first step always is we want to make sure that we balance the equation. So once we balance the equation, and again, nothing's going to work out right if you don't start with that equation that's balanced. The next thing that you want to do really is convert what they gave you to moles. So in this case, we're only given really grams of H2O, which means what we would want to do is, in sort of this step here, is convert those grams of H2O to moles. And again, to do that, we would go to the periodic table, look up the molar mass of for water, which is 2 hydrogens and 1 oxygen, which means the molar mass of water would be 2 times 1.008 plus 16 for our oxygen will give you 18.02 grams per mole. And again, this is where we would be using our conversion factor here. So we would start with our 52.0 grams of H2O. Again, just doing a simple conversion of grams to moles for the molar mass. And if we do that here, we end up with something roughly 2.886, we'll call it, moles of water. So that is typically your first step or your second step that you do after you have the balanced equation. At this point, we pretty much have just kind of converted into moles. We converted whatever they gave us in moles. And the purpose of that is because we're now going to do really the stoichiometry part, which means we need to go to the equation and find the mole to mole relationship that we're interested in. So where we are and what we were given in this particular problem, for example, is we were given information about water, but we're definitely not interested in water. We're actually interested in the final sort of part of the problem, oxygen. So this is really what the stoichiometry is. Again, you can't go to a table and go, what is the relationship between water and O2, right? There's no such conversion. So where we find that conversion is from the balanced equation. So we really are not interested in water, but we need a way to go from water over to the O2. And that is where we would find the O2 and water relationship that we got from the equation, which was in this example, this relationship. And remember, from this relationship, it gave us 2 conversion factors that we potentially could use. So what one we want to use in this case? Well, we are in water and we want to get rid of water. So like a normal conversion, what we want to do is go opposite. So we would want to use the conversion factor where water is on the bottom. So we would want to use this guy on the left. Again, as I mentioned earlier, you typically don't use both of them. Otherwise, probably something's wrong here, but we would use that one. And that would be the third step. That's the stoichiometry step. That's the step that people get all freaked out about. Like, I'm not sure what to do. But it really is just simply going to the balanced equation, finding yourself the 2 things you're interested in. The 2 things you're interested in is, one is what they gave you. The other thing is basically what you're trying to find. So continuing on with our calculation here in my problem, we would get 2.886 moles of water. Now we're going to, again, use our relationship to go from water to O2. So we want to get rid of water, which means on the bottom from the balanced equation, which is the stoichiometry part here, 2 moles of water gives us 1 mole of O2. That is the stoichiometry conversion. That is what's going to allow us to go from one thing in the equation to another. So we're basically just dividing it here by 2. And we end up with 1.443 moles of O2. So by doing this, we have now successfully used the equation to go from water, which we're really not interested in, but it was the only piece of information given to us, to O2, which is obviously what we're interested in. So we're very close. In some cases and problems, this could be the end of the problem. And that would be a case where they asked about how many moles, right, you would need. And if it was asked about how many moles, then you would technically be done at this point. But we weren't interested in moles. We are interested in grams in this particular problem. So in a lot of steps, our basic stoichiometry problems, you need to go one more step, which is step number 4 typically. And because after you did step number 3, you will always be in moles, you typically at step number 4, a lot of times need to take those moles and convert them to some other unit. So again, that could be grams, could be pounds, could be some weird unit or something like that. But in a lot of cases, it is grams. So a lot of times, again, on the back end of the calculation, like I mentioned before, we oftentimes need to go from moles to grams. And if that was the case here, we are actually going to take our moles that we had above, which is 1.443. And the important part, though, is we got to remember that we have now done our stoichiometry and our conversion. So we're no longer talking about water at this point. We're talking about oxygen, which is a common mistake sometimes people make. We actually now need the molar mass of oxygen to do this. And the molar mass of oxygen obviously is 2 times 16, which is 32 grams per mole. So here we would actually multiply by 32 up on top. Moles on the bottom. The moles will cancel. Sort of missed there. And we will end up with here, looks like 46.2 grams of oxygen. And when you're dealing with sort of basic stoichiometry problems, these are really the same 4 steps that you do pretty much over and over again. If something is done for you, you obviously just kind of skip ahead. You don't want to undo it. I've seen it before. For example, if you're given information in moles, you don't need to convert them to moles or unconvert them and then reconvert them, which oddly I've seen people do before. You obviously would just continue on to the next step. So these are the 4 basic steps here. And basically the idea here of stoichiometry is you're given some piece of information about somebody in the equation that you're really not interested in, but you need a way to, again, sort of go from that guy to somebody else in the equation. And it's that kind of 3rd step and that stoichiometry step where we use the mole-to-mole relationship that basically allows us to do that. Any questions on kind of basic stoichiometry sort of problems here? Okay. So as I mentioned before, these are sort of the 4 kind of steps that we just talked about there. Again, nothing works correctly for sure in this type of process if you're not starting with a balanced equation. So kind of as we talked about when we're talking about balancing equations, I would say probably in most cases, if you see an equation and you see some coefficients written, some numbers in front of people, probably it's balanced. Probably a good idea to check. Definitely if you're given an equation, you don't see any coefficients, you should definitely check to make sure it is balanced. But you definitely want to make sure that it's balanced. So you could even have a problem again where everything's in words. So just like we talked about when we talk about balancing equations, you want to make sure that you start with the proper formulas. You want to then make sure you balance it, and then you should be good to go in a stoichiometry problem. Again, because the basis of stoichiometry is based off of those coefficients. If you do not balance that equation right, you're just setting yourself up, obviously, for I would say disaster sounds bad, but you're setting yourself up for probably not doing the problem correctly. Then number 2, again, really important as well. We pretty much want to get whatever they gave us into moles. And again, a lot of times that will be the sort of grams to mole conversion. But, there are other units that you may be given in terms of, kind of starting amounts. You may be given something again in something like pounds or kilograms or something like that. But again, however many conversions you need to do, you just need to eventually get those guys into moles. And then, as we talked about, use the coefficients. That's that mole to mole relationship from the balance equation. And again, we could use our molar mass there to do that. And lastly, once we do that, convert to whatever units we're looking for. So these 4 steps, again, are very sort of crucial in doing these type of problems. And what does stoichiometry problems allow us to do? So again, it basically allows us to understand what should be sort of produced and how much you need in a particular reaction. So for example, in my made up problem here, basically what we calculated there with the 46.2 grams of oxygen is if I technically wanted to produce 52 grams of water, or I produced 52 grams of water, that meant that I had to started with pretty much 46.2 grams of oxygen. And again, we kind of went in terms of stoichiometry. For example, we'll look at this guy again. 2H2 plus O2, 2H2. In the particular example, I did before, we went from products to reactants in terms of the calculation, which is perfectly fine. A lot of problems you start with reactants and you figure out how much products. So a lot of times you go reactants to products. And again, if you know how much you started with, it will tell you if everything went great, how much you should produce. Now, sometimes people are confused. You have to go kind of left to right across the arrow or right to left across the arrow. And the answer is yes, you could do that. The other thing is you may not even have to cross over the arrow. You could do the relationship between reactants to reactants as well. So you could do stoichiometry involving just everybody on the reactant side. In this case, we don't have a second product, but if you did have, you know, something like this, you could also do the relationship between products to products. So it's very sort of, I guess, powerful in that sense, because if you just pretty much know one piece of information, you could use the balance equation to pretty much figure out everybody else involved. So for example, if I knew how much of one product I produced, I then could use stoichiometry to figure out how much of the other product would be produced. Same thing with the reactant. If I know how much of one reactant I need to put in there, I could use stoichiometry to figure out how much of the other reactant I need to put in there. So you pretty much can use stoichiometry kind of, I call it across the arrow, go from reactants to products or products to reactants. You can also use stoichiometry in those relationships on the same side of the arrow, all reactant to reactant relationship or product to product relationship. So sometimes people, when they kind of first learn stoichiometry or deal with stoichiometry, they always think that you kind of has to always go in one direction, like reactions to products, that sort of, you has to cross over the arrow for that relationship or to use that stoichiometry relationship. And again, it's not the case. You can pretty much do it like we just see here, going to one side of the arrow to the other or staying on one side of the arrow. Any questions on that? And again, in basic stoichiometry problems, pretty much the same 4 steps, regardless of if you're going across the arrow to do those relationships or staying on the same side of the arrow, it's still the same 4 relationships. All right, so we talked about those, I think. All right, so why don't you take a couple minutes here and see what you come up with, and then we will discuss it. But while we try this problem here, methanol burns according to this equation. If we started with 209 grams of methanol, what is the mass of water produced? And the mass meaning we'll go with grams of water produced. And so take a few minutes. I'm going to give you some numbers in case you don't have a periodic table there yet. Assume you do, but 12 grams per mole. Hydrogen is 1.008 grams per mole. I think we've got some oxygen in there as well. 16 grams per mole. All right, so give it a try here, see what you come up with. Again, follow those 4 steps that we just talked about, and hopefully we'll end up with the same answer here in a couple minutes. Let's take a look, see how we're doing. So again, in a basic stoichiometry problem, and I'll explain what makes this sort of a basic stoichiometry problem here in just a second. We do want to follow the same sort of 4 steps. What makes it a sort of a basic stoichiometry problem, and how I sort of describe it, is when we look at this, we're really only given one piece of information, which is methanol, which, by the way, is this guy here. We're not really given any other information in this problem. We're asked to find, in this case, how much water we would produce in this case. And that's what I consider sort of a basic stoichiometry problem. You're really only given one piece of information. You're either given some type of piece of information about your reactant, some piece of information about your product, but that's pretty much it. And in that case, you pretty much can roll with our kind of 4 steps here for our basic stoichiometry problem. So the first step is, as we talked about, it is to balance the equation, which clearly I see coefficients there. So I'm going to probably safely assume that it is correctly balanced. You can double check, but it is correctly balanced. The next thing that we want to do, right, is take whatever they gave us and convert to moles. And in this case, we're only given 209 grams of methanol, which means we do want to convert our 209 grams of CH3, oops, too many C's there, CH3OH. Try that again. All right. CH3OH, there we go. In order to do that, as we talked about before, we do need the molar mass of methanol there. And again, the molar mass of CH3OH means that we should have 12.01 for our carbon. There's actually 4 total hydrogens there, 1.008. And then there is 1 oxygen at 16 grams per mole. So if we add all those guys together there, looks like we end up with about 3204 grams per mole, which again is really our conversion factor that we get from the periodic table to convert from grams to moles. In this case, we do want to obviously put the grams on the bottom so that they cancel. So that means we're going to divide by 3204 grams per mole of CH3OH. That's going to get rid of the grams. And we will end up, if you got a number at this point, we'll take it to a few digits and not round too much at this point. Looks like 6.5231 moles of methanol. Now, remember that that's good. We now got it into moles, and now we can go to our mole to mole relationship from the balance equation. So remember, when we're doing that, the 2 things we are interested in is obviously one thing that they gave us, which was this guy, and what we are trying to find, which is this guy over here. So that is the mole to mole relationship that we are looking for. That is also why we had to do step number 1 and convert things into moles. And from the equation there, we do see that the mole to mole relationship is, from the equation, for every 2 moles of methanol I throw in there, I am going to get, looks like 4 moles of water out. So that's the mole to mole relationship, again coming directly from the coefficients in the balanced equation. And remember, pretty much like we talked about from that equality, you can write 2 conversion factors. We could say for every 2 moles of our methanol, we have 4 moles of water, are basically the opposite. 4 moles of water on top and 2 moles of methanol here on the bottom. Since we are in moles of methanol at this point, and we do want it to end up with water when it's all said and done, that means that we do want to actually use the conversion factor here on the right-hand side. And that would really be our third step here. Again, continuing on with our number from above. This is really the stoichiometry part of the calculation. Again, setting it up dimensional analysis way so you can see the units cancel. 2 moles of methanol on the bottom, so they do cancel. 4 moles of water up on top. Moles are going to cancel. And that will end up with about 13. Again, it won't round too much at this point. 13.046 moles of water. Any questions up to that point there? Well, we're close to what we want. We would be done if we were obviously looking for moles, but we're not looking for moles. So what's left is very commonly in these problems, that last step that we want to do, which is really just going now from moles in this case to grams. So we do need the molar mass to do that. Important to remember again at this point, we have now converted into water, which means we do need the molar mass of water, which we calculated earlier as doing this. (18.02 grams per mole). So our last step, again, continuing with our number here. In this case, we're going to put the 1802 grams on the bottom so they cancel. Basically, we're dividing by it. Grams will cancel. And at this point, if we, I'm sorry, I put that backwards, didn't I? Yes, I did. Hang on a sec. Take 2. That would be right if we were starting with grams, but then we wouldn't need to be doing that conversion. Let's try that again. That is actually moles there. There we go. Which means opposite of that, I'm sorry, multiplying by 18.02 grams per mole. We wouldn't need to be doing that then in this case. There we go. All right. So try that again. So let's see here. We're going to take that and times it by 18.02. And that would get us something like 235 grams of water here. At this point, I'm going to round it to 3 significant figures because really the only number given to us is this number here, which is 3 significant figures. So that's why I would round my answer. First off, any questions on any of the 4 steps there along the way? I will say that I obviously broke it up here into individual steps. I broke it up, getting an answer after every step, which is perfectly fine to do. If you do it this way, like I did it here, you do want to avoid a lot of rounding after each answer. I personally didn't round it all on my calculator. I just kept all the numbers and kept going. But you do want to avoid rounding along here. You absolutely could do this all in one sort of calculation. You could set up this sort of calculation followed by this conversion, followed by this conversion, and get the answer and do it all together. That is perfectly fine to do. I just here broke it up so you can see each of the steps sort of separately. So the question is, why in the last step is it not 4 moles of H2O? So I think I understand your question. So let me answer it this way. And it's actually back to, if you remember, something we talked about, I think when we were talking about actually calculating molar mass and stuff like that. So remember that when you are asked to calculate the molar mass of something, and I'm assuming you're wondering why we didn't put the 4 here, right? The reason we don't do that is whenever you're asked to calculate the molar mass, it is always based on the formula, which means 1 mole of it. And that's why molar mass units are grams per mole. So when we do the molar mass of something, the number stays with the grams, but it's always 1 mole. which basically means that it's always based on just the formula, not the coefficient in the balance equations. And the reason for that is we don't do that in this particular case because we actually took the 4 into account when we did this step here. Now, if you took the 4 into account when you do this step as well, now you over forwarded it, if you will. You did it too many times. So whenever in any situation, regardless if you have an equation like this and you got some coefficients, when you calculate the molar mass, it's always based on just the formula. And that's why earlier when we did the molar mass of this guy, even though there was a 2 here, it again is just based off of the formula, because anything in terms of an equation that you have a balanced equation, you got those kind of coefficients in front, is probably, if you're going to do some type of calculation with it, will involve stoichiometry. And when we do stoichiometry, we take care of all the coefficients in this step. That's basically where all those 4s and the 2s get taken care of, sort of in that step right there. So if you do it in that step, like step number 3, and you also do it in your molar masses, you're technically overdoing it in that sense, and you will get the wrong answer. So the simplest way to think about it is whenever you need to calculate the molar mass of something, even if it's in an equation like this, regardless of what it is, you do it simply based off of the formula that's there, one of the formulas that are present. Other question, that's a good question, is it's a very common mistake that people do in stoichiometry is either they don't really, I guess the way where even though they screwed up the calculation, they still maybe will come out okay, is they kind of don't do this or do this part badly and then kind of incorporate the stoichiometry here. Where most people really do mess up is they kind of do the stoichiometry here and then kind of put the stoichiometry in here because of those coefficients. So you definitely always, regardless of the coefficient, molar mass simply based off formula. Leave the coefficients for the step number 3 here, the stoichiometry part of it. Other questions? All right. So why don't we take a look at, we do another one here, and we're not going to do the same problem here. Let us do, we'll cross all this out. Let's say let's see this one. Let's say we started with 125 grams of O2. How many grams of methanol is needed? All right, so we'll use the same formula here, our equation. We use the same equation, obviously same molar masses and those type of guys. Take a couple minutes, see what you come up with here. Again, same numbers as in the previous problem. All right, let's take a look at this. So again, really, if we look at the problem, we're only given one piece of information. So again, this sort of classifies as a basic sort of stoichiometry problem. We're obviously given in this case information about O2. We're given information about this guy, but ultimately we do want to get to this guy in the equation. And again, we're going to allow stoichiometry to do that for us. So same sort of steps here. We've obviously balanced the equation as previously. We are given something in grams, so we do need to do that conversion to moles. So we want to convert to moles here. And again, in this case, we're starting with O2, so we would want to do that conversion first. So we used O2, I think, in the previous calculation, and that is 32 grams per mole, which would be the molar mass of O2. And again, as we just discussed, we always want to make sure molar mass part of any conversion is just based off of the formula, and that's where we get the 32. And if we do that, there looks like we will end up with 25 divided by 32. And again, here, you could do this all in one step, or you could get an answer like what I'm doing. And again, I wouldn't necessarily round too much if you do get an answer, so you don't find yourself too far off there. At this point, we have now gone to moles of O2. Again, we're not interested in O2. We are interested in this methanol, so we need that relationship. And from the equation, we see that for every 2 moles of methanol that we put in there, which is the coefficient, we get 3 moles of O2, which is also the coefficient. And again, that does give us two options in terms of conversion factors: 2 moles of methanol over 3 moles of O2, or our 3 moles of O2 and 2 moles of methanol. In this particular case, we have O2, we want to get rid of it, so we will use the conversion factor there on the left-hand side. So if we continue on here with our calculation, getting rid of the O2, we're going to go with 3 moles of O2 on the bottom and 2 moles of methanol up on top. This is the big stoichiometry part, or the third part where we do the mole to mole relationship. Again, that's going to cancel out the moles of oxygen, allow us to successfully convert over to our methanol here. And if we do that, it looks like we're going to multiply by 2 and divide by 3. It looks like 2.604 moles of methanol. Again, if we were asked just about moles, we put a box on it and we would be done. But again, here we are looking for grams. So we do have to do that fourth step, which means that we would need the molar mass of methanol, which we also calculated in the previous problem. So we'll just use that number. Obviously, it's the same. And using the number there from the previous problem. And again, the molar mass just from the formula, the CH3OH, regardless of the coefficient, because we already took that into account over here. We will then do our fourth step, which is kind of convert things from moles to some other unit. And it looks like we do end up with about 83.4 grams. 83.4 grams of methanol in this particular case. And again, 3 sig figs based off of really 3 sig figs on that number there. You can hopefully see a pattern here. It really is the same 4 steps, regardless of sort of where you're going in terms of the stoichiometry part, if it is a basic stoichiometry part. Any questions on basic stoichiometry problems here? So what do some of these numbers mean before we kind of move on from this part? Well, what this problem means in this particular case, because we're really looking at sort of reactant and reactant, right? O2 is a reactant, methanol is a reactant. Basically what it's telling us is if we decided to put in there 125 grams of O2 to start this reaction, in order to probably successfully use up all 125 grams of O2, we would need to put in there about 83.4 grams of methanol to react properly and sort of use up all of the grams of O2 that we started with. In the previous problem, we figured out, how many grams of water. And in this problem, what this is if we started with 209 grams of methanol in the previous problem, and everything went perfect. There was no side reactions. You weren't a klutz and dropped everything everywhere on the floor. If everything went perfect, based on starting with 209 grams of methanol in the previous problem, everything went perfect, we should, in theory, be able to produce 235 grams of water. And because water is a product, and what we calculate down here is basically how much of that product we should be able to calculate, this is what is sometimes referred to as the theoretical yield. Hence, in theory, we should produce that much. It is like your maximum amount that you should produce if everything went perfect. In reality, things don't go perfect all the time, but you know, it's basically your kind of theoretical goal that you could hit. In our really way back problem here that we did, we ended up with 46.2 grams of O2. What this told us based on this first calculation was if we produced the 52 grams of water, we would have had to started with 46.2 grams of oxygen to put in that reaction. So again, these calculations you could do for really anybody involved, reactions, products, and it does give you that type of information. Like, if we produce so much like we did here in this problem, this is how much reactants we need to put in there. If we started with a certain amount of reactants, this is how much products we should produce. So it gives you all that really kind of important information. Any questions on basic stoichiometry type problems here? Now, when we talk about sort of basic stoichiometry problems, it really is these type of problems here where we're given really, as I mentioned, information about just one thing in the equation. It could be a product, could be a reactant given to you. But there are certain times where we do come across stoichiometry problems that are, I guess, a little bit more complicated in a sense. And that's when we're involving, we're sometimes referred to as limiting reagents. And limiting reagents here, just get this is kind of what we did there on that calculator. And again, here, as I was mentioned before, you could do it all in one sort of step, like we did here, and not get an answer in between. And again, it's just the same calculation we did. It's basically our step 1, 2, 3, and 4 here. So again, this is what I was talking about earlier. You could just, do all these steps together in one big calculation perfectly fine, and you should get the same answer. If you do it kind of step by step like we did previously, as I mentioned, you just want to avoid kind of the rounding, extreme rounding in between. Now, when we deal with limiting reagents, what that means is when we do a reaction, there's always some reactant that basically gets used up first, and that is the limiting reagent. So the limiting reagent, or sometimes referred to as limiting reactant, the limiting reagent is basically the reagent that gets used up first. Then that means that there is another reagent that you have plenty of, and that is the excess reagent, where you have plenty of it. You have some left over when it's all said and done. So we have a limiting reagent and we have an excess reagent. And in this particular example here, we do have the NO is our, oops, come here. The NO is our limiting reagent and the O2 is our excess reagent. The NO is kind of the red and blue circles is the NO, and the 2 blue circles is the O2. And you can see that when we get down to our products here, there's no more NO circles, right? No kind of red and blue circles there. There is O2 circles, which tells us we have some of those left over. So that's our excess reagent. And we'd obviously have these guys, which are our product that was formed, right? So why is it important limiting reagent versus, say, excess reagent, or even worrying about that? Well, if we take just a very simple sort of example, we take A plus B to make A and B, right, which is our product here. And let's say that A was our limiting reagent, and let's say that B was our excess reagent in this case. What happens is, in order to make our product, we basically need one A and one B to come together, basically, right, to make AB. The problem is, though, that when our limiting reagent runs out, we no longer have any A. which makes it absolutely impossible to make product at this point. You can make a lot of B's, but you can't make an A and a B because you no longer have any of that reagent still there. So it is always the limiting reagent that determines how much product you can make. Because once that limiting reagent pretty much runs out, there's no possibility that you can make any more product. And that's what we see over here. O2 has obviously just oxygens. NO has a nitrogen and an oxygen, which means once all of our NO runs out, there's no possible way to make any NO2 because we don't have the needed nitrogen in this example. They're all gone. We do have, again, plenty of O2 left over, which is another common question that you're sometimes asked in these type of problems is how much of your excess reagent do you have left over? In this case, we could simply count. We got like 3 O2 molecules basically left over. So it's always the limiting reagent that determines how much product you can make. It's kind of like, I think they still do that. Like when you buy hot dogs, a package of hot dogs and like a package of hot dog buns, I think you get like 8 hot dog buns and like 10 hot dogs. So at some point, you're going to run out of buns, right, to put the hot dogs in. The buns would be your limiting reagent. And if you had 8 hot dog buns and 10 hot dogs, you would have 2 hot dogs left over, and the hot dogs would be your excess reagent. So, these are very common sort of problems, or things that you're asked. How do you know it's sort of a more complicated, I don't say complicated, but a little bit more process or a different process, if you will, type of problem or limiting reagent problem versus a basic stoichiometry problem? The way that you can definitely tell the difference is, first off, if you think about all the examples we just did in sort of those basic stoichiometry problems, we were only given really one piece of information. We were either given, how much of our reactant we started with, how much of our product we ended up with, but really only one piece of information. The way you can recognize these things as a limiting reagent problem is you're given enough information to get to moles of both reactants. So first off, you're typically only given obviously reactants because it's a limiting reagent type problem or reactant type problem, but you're given enough information, and that information could be different types of information, but there's a way for you to, based on the information given to you, figure out the moles of each of the starting reactants. And if you do, it is a limiting reagent problem, which means there's many ways that you could solve a limiting reagent problem. You could follow the same sort of steps as what we talked about before. The only difference is you need to add a step where you figure out which one is the limiting reagent. So let's talk about sort of how to do these problems. And I'm going to show you a way that is a little bit different probably than something you've learned before. So if you've learned about limiting reagents or reactants before and how to solve them, like I said before, there are many different approaches that you could take to solve these things. We'll talk about a couple different approaches, ones that are probably familiar with you, and we're going to talk about one where maybe it's not so familiar with you, but there is some benefits of the way I'm going to show you how to do these problems. First off, the first benefit is if you plan on taking 200B, this will be a very similar calculation that you'll do all the way through 200B. Secondly, it's kind of convenient, this method I'm going to show you, because you could very much and really quickly answer every type of question that could be asked to you in almost like a 1 or 2 step type of approach afterwards. So it allows you to kind of quickly answer every type of question. Common questions that you're asked is, how much of all the products you're producing. Other common questions are, how much of that excess reagents left over. So the method I'm going to show you allows you to, kind of quickly go back and really determine, all those sort of answers without necessarily having to go maybe all the way back to the beginning and start a whole separate calculation. You kind of continue on and answer those questions. So just up front, I'll say typically in limiting reagent problems, there's 2 very common methods that people have been taught. One method is that you do 2 separate calculations, one with each reactant and figure out how much product each one would make. And whichever one makes the smallest number of products or smallest amount of products in terms of grams, that is your limiting reagent and your theoretical yield. So that's a very common approach to solve these problems, is simply just do 2 separate stoichiometry problems, one from each reactant to the product, and see how much each one makes, and whichever one's the smallest is your answer in terms of how much would be produced and which one's your limiting reagent. Again, the problem with necessarily that method is if you're asked something like how much is left over, you then need to go back and kind of do some more calculations and sort of figure that out as well. Another very common approach, which I think is a second way I'll kind of show you here, is you take both reactants and you do a calculation to figure out if you want to use up all of one of the reactants, how much of the other reactant do you need to put in there? And then you kind of see, do you have enough? And if you do, then that's the excess reagent. If you don't, then that's the limiting reagent. So those are 2 very common sort of approaches. The approach I'm going to talk about here first and show you is what is sometimes referred to as doing this using a ICE table. Now, ICE table in our case here basically stands for initial change, and we call it end here. If you take 200B, you call it equilibrium, but here we'll call it end. And the idea here is we represent the change is represented with an X, like an unknown sort of variable, if you will. So the first couple of steps when we do this type of problem is really the same couple of steps. Is you might always make sure you got your balanced equation, just like we talked about before. You got to also convert what they gave you to grams. So when we read a problem like this, that we're taking 124 grams of aluminum and we're reacting it with 601 grams of iron 3 oxide, how much mass or grams of aluminum oxide are produced? Right off the bat, I see I am given 124 grams of aluminum, which is this guy. I also see that I'm given 601 grams of iron 3 oxide, which is this guy. I have the grams of each of these guys, which means I definitely know I could get to the moles of each of these guys. So because I was given the starting amounts of each reactant and I'm able to get to moles, this is how I know that this is a limiting reagent problem. Again, I have the starting amounts of both reactants, and I could get both of those reactants into moles pretty easily without any piece of information. So that is definitely how you first could recognize that this is a limiting reagent problem. I have both of those guys. I could get them into moles. So we're going to kind of do this like we talked about. So here, first off, it is balanced because we do see some coefficients. The next thing that we want to do is just like before, we want to convert into moles. So in this case, we have 2 things to convert into moles. We have 124 grams of aluminum. We would need to go to the periodic table and look up aluminum. And we see on the periodic table that aluminum is 2698 grams per mole. That will give us our starting amount for aluminum in terms of moles, 124 divided by 26.98 of 4.596 moles of aluminum. We also would want to do the same thing for our other reactant, which is 601 grams of iron 3 oxide. Again, in this case, we would need to go to the periodic table there, and we would need to take 2 times the molar mass of iron, which is 5585, plus 3 times the molar mass of oxygen, which is 16. And that will get us a molar mass for iron 3 oxide of 159.7 grams per mole. And again, that is from the periodic table, 2 times 5585 plus 3 times 16 for the oxygen. All right. And if we do that conversion there, it looks like, and again, just to make sure I typed it in right, I think I did. It looks like we will end up with 3.763 moles of our other reactant, iron 3 oxide. So again, this is definitely how we recognize this as a limiting reagent problem. You can see just based on the information given to us and the periodic table, we were able to get to moles of both reactants. And again, that is a absolutely big hint that this is a limiting reagent problem. And somewhere along the way, you do need to determine which one is the limiting reagent. Any questions so far? All right, so this couple of steps, again, pretty much identical to what we do in basic stoichiometry problems. Also, truthfully, kind of identical to what you do in any type of way to solve limiting reagent problems. Now, what we're going to do next is the ICE table, and this is going to allow us really to figure out everything. And this is, again, probably something different than how you learned it. But again, there's a lot of benefits to sort of doing it this way. So to do the ICE table, we're going to simply, in this case, since the equation is up there, I'm going to rewrite the equation here, which is 2 aluminum plus our iron 3 oxide goes to our aluminum oxide plus our couple of iron. All right, and we're going to basically start our ICE table with our I. I stands for initial moles, basically. So we calculated that. So for aluminum, it is 4.596 moles. For iron 3 oxide, it is 3.763 moles. And in a case like this, we can initially assume that we have no products, right? This reaction needs to go to the product side to make products. So initially, we're going to assume that we have nothing on the product side. Any questions on that? Now, the change part is really important because the change part is basically going to tell us what is happening in terms of our sort of reactants, how much we're using, and all that kind of stuff. The first thing is when we look at an equation like this, it is assumed that this reaction is going from reactants to products, right? So what does that mean? Well, it means that if we assume this reaction is going from left to right, we would expect the amount of reactants to decrease, right? And we would expect the amount of products to increase, right? Considering we're starting with 0, so it's got to go nowhere else to go but up. And in order to make our products, we need to use up our reactants. So the way that we represent the change, as I mentioned before, is with X. And when we go on the reactant side, typically it's minus X's. And on the product side, it's plus X's. Again, minus because reactants should be decreasing, plus because products should be increasing with time. The other really important thing is this is stoichiometry, which means we need the mole-to-mole relationship. And it is in this step where we do the change part that we actually take into account that mole-to-mole relationship. And we do that with our X. So if we start here with aluminum, and we're going to do the change part, aluminum, which is a reactant, should be decreasing with time, which means I'm going to go minus. The coefficient here in front of aluminum is 2, and this is going to be minus 2x. The x is the change. The 2 here takes care of the mole to mole relationship, and the 2 came right here from the coefficient. So minus, because it's a reactant, should be decreasing. 2 is there to maintain our mole to mole relationship, and x is going to be our change part. Any questions on that part there? That means when we come to our next guy, which is iron 3 oxide, again, that's a reactant, so it should be decreasing, so minus. Coefficient here is 1. Don't really need to write 1 if you want. And x. So this is basically minus 1x. And again, here minus because it should be decreasing. 1, which you don't need to write. If you can, I guess, if you want, but you don't need to. 1, which is, again, the coefficient. And x, obviously, is the change part. Now, when we go to our product side, as we were talking about, our product side, we should expect these guys to be increasing with time. As time goes on, we should be making products. We're going to represent those with positives here. So as we come to our aluminum oxide on the product side, this should be plus because we're making products. Coefficient here again is 1. So we don't need to write it, and this would just be plus x or plus 1x if you want to be specific. Our iron is another product which should be increasing with time, which again means that we should have a plus. And again, we are going to go with a 2 here to maintain our mole to mole relationship from the coefficient, and x. Any questions on the change part? Okay. Now that we have the change part, we're going to get to the end part here. And the end part is pretty much just going to carry down everything above it. So the end part is we're just going to carry down the numbers. So 4.596 minus 2x. And get rid of the moles. Just remember everything's in moles at this point, just to make it a little bit clearer here. Minus x, x, and 2x. Any questions here? And again, a reminder that when we solve for x in this case, it is moles is the units that we're talking about here. So what we need to do is we have this all set up. We still haven't really figured out which one is our limiting reagent and which one is our excess reagent. So we could do that by 2 very kind of simple calculations. What we're going to do now is we're going to take each of our reactants that we got on the end part, and we're going to simply set them equal to 0. So if I take my first guy and go 4.596 minus 2x is equal to 0, I'm going to bring the 2x to the other side. Divide by 2, we get x is equal to 2.298 moles. We could do the same thing for this guy, 3.763 minus x is equal to 0. Bring the x to the other side. We get x is equal to 3.763. And again, the units here would be moles. At this point, what we are looking for is the smallest x value. The smallest x value will be your limiting reagent. So in our particular case, the smallest x value is this guy here. And that means that you really don't need this guy. And now we're good to go to fairly quickly answer every question that we may be asked to do. So let us start with, what does that x represent? So The X that we just calculated right there, this X, is every single X that is here in the end line. And at that point, we now have information about pretty much everybody that we need. So let's start with the actual question, which was how much aluminum oxide would be produced. If we go to aluminum oxide, and I grab a pen, I think. If we go to aluminum oxide, we see that at the end, it equals X. And what that means is the moles of aluminum oxide would equal X, which in our case would equal 2.298 moles of aluminum oxide, which if we were interested in moles, we would be done. We could put a box on it. But we're interested in grams, so we do need the molar mass of aluminum oxide. So aluminum is 2698, and there are 2 of them, plus 3 times 16 for the oxygen gives us 101, we'll call it 102 grams. So we could go 2.298 moles of aluminum oxide using the molar mass, which rounding gets you about 102 grams per mole. Tells us that we made about 234 grams of aluminum oxide, and that would be a theoretical yield. Any questions on that so far? Now, in this question, that was really all we were asked. And again, if you took like a second sort of method to do these type of problems, and you did 2 separate calculations to the product there from each of the reactants, you would end up with 234 as your smallest number. That would be your answer. Where this sort of method really, I think, is beneficial is what happens if we had a problem where we were not just interested, for example, in the mass of aluminum oxide produced, but what happens if we also wanted to know how much iron would be produced? Well, at this point, we can go and very quickly go, okay, you want to know how much iron is produced? Iron at the end, moles of iron is equal to 2 times X. So if we put that in there, that's 2 times our X value, same X value, 2.298 moles of iron would tell us that in addition to our aluminum, we would produce 4.596 moles of iron, which if we wanted how many grams that would be, we could go to the periodic table and we see iron is 5585 grams per mole. And we would produce about, we'll call it 257 grams of iron. This would also be, by the way, a theoretical yield. And you can see here that, relatively quickly, in addition to figuring out how much aluminum was produced, we could very quickly figure out how much iron was also produced as well. And the next thing that we could figure out, which is a very, very common question, is remember that we figured out that our aluminum here was the limiting reagent. By default, by the way, that means that our excess reagent is the iron 3 oxide. A very common question in sort of limiting reagent problems is how much product you're going to produce. Then it is how much of your excess reagent is left over. So again, by doing this method, and we know that the iron 3 oxide is our excess reagent, we can again very quickly use our ice table here and figure out how much of that would be left over. So we know that the moles of our iron 3 oxide left over is equal to 3.763 moles minus X, which means 3.763 minus our x value. Again, exact same x value because it's the same number all the way across. And we can very quickly figure out that we would have left over 1.465 moles of our iron 3 oxide using the molar mass of iron 3 oxide that we had earlier, which was right here, 159.7 grams per mole, would tell us that we would end up with about 234 grams of iron 3 oxide that was left over. And you can see we don't have to necessarily go all the way back to the beginning to do a separate calculation for something like that. We can very quickly sort of determine all the things that we would want to know. What would happen if we put the x value into here? Well, it would essentially equal 0, right? Because it's the limiting reagent and it should zero out. So what we were able to calculate really quickly after sort of getting our ice table all set up and figuring out what x is we were able to figure out, how much of each product we would produce. We were also able to figure out how much of our excess reagents left over. So remember that our excess reagent in this case was the iron 3 oxide. We started with 601 grams of it. We have about 234 grams of it left over. That's roughly, whatever it is, 360 some odd grams was used up in this particular reaction. Any questions on any of those sort of steps? Okay. So again, this is perhaps a new approach for you. Again, the benefits of it is what I just showed you. You can relatively very quickly figure out how much of everybody is there or what's going on, with everybody that's in this problem without necessarily having to go all the way back to the beginning and sort of do a separate calculation. You can kind of just continue on with your calculation and it puts everything sort of in a convenient location for you to do that. All right, so we will lay it up here for lecturing right now.